Can you see my sharing?
No, ma'am.
No, ma'am.
Yes, ma'am. Now you can.
Can you see? Sorry.
Yes, ma'am. We can see now.
Okay, you can see my slide.
Yes, ma'am.
Do you still see the Google Meet thing in the bottom right corner, or are you seeing a clean slide?
Yes, ma'am. We can see the Google Meet at right bottom corner.
Okay. Now, is
Yes,
it
ma'am. Now
gone?
fine. Yes, ma'am.
Okay. All right. And I'm trying to see whether you can see my cursor. Are you able to see?
No, ma'am.
Now
Yes,
can
ma'am. Now
you?
we can see. Yes, ma'am.
Okay. Okay. So thank you very much for this opportunity, and I hope to give you a few glimpses of what research on the cosmos with respect to giant black holes is telling us. So to start with, I want to play a little game with you using ideas from Newtonian physics, which I think all of you might remember learning about in your high school. Okay, so you probably remember the idea of escape speed. Now, suppose you imagine that we squeeze the Earth and we squeeze all of the mass of the Earth so much that the escape speed from the Earth, instead of being 11 kilometers a second, actually becomes equal to the speed of light. So if we do that, then we get a black hole because nothing can escape from it, not even light, right? So in terms of formulae, this is what it would look like. You probably remember this formula from high school, which was the formula for the escape speed. Now, instead of the speed of light, if you replace that, instead of the speed of the object that is trying to escape, if you replace that by the speed of light, then you get this formula. And so then it becomes a relationship between the size of the object from which we're trying to escape and the mass of that object. So if this relationship is satisfied, it means that the escape speed is the speed of light, and so nothing can escape. So effectively, it is a black hole. So for the Earth, if you want to hypothetically convert the Earth into a black hole, it turns out that we have to squeeze it to marble size, meaning all of the mass of the Earth has to be squeezed to marble size, and then it will become a black hole. Now you'll say that that is almost impossible. You're kind of correct. Suppose we think of the sun instead of the Earth. Then it turns out, as per this formula, it turns out that you just have to squeeze it, all of the mass of the sun, which is of course enormous, to about 6 kilometers diameter. Now that is a bit less of a squeeze, right? And then if you think about Gargantua, which was the fictitious black hole in the film Interstellar, that had a mass of 100 million solar masses. So by the way, this symbol M with that symbol beneath it, that is the symbol we use to designate the mass of the sun, and we use that as a unit of mass for things in the cosmos. So Gargantua had a mass of 100 million solar masses, and so then squeezing that so that its escape speed is the speed of light is much less of a squeeze. So then it becomes much more realistic. Okay, so before getting into the details of what research in black holes are like, I just wanted to give you a summary of some of the preliminaries. So, in astrophysics, we have basically four approaches to research. One is theoretical predictions, the other is building instrumentation, the third is observing the sky to test these predictions, and finally, we also do computer simulations to compare with observations to get a more to look for consistencies and see whether our understanding of the physics as we put it into our computers is correct. So some examples of theoretical predictions are, for instance, in as early as 1600, um, somebody called Giordano Bruno in Italy contemplated the cosmos, and he said that other stars must have planets. Now, this was a completely speculative idea at the time because he did not have access to telescopes and so on and so forth, and there was no way he could have seen planets from other stars anyway. But today, over the last several years, this is a very, very hot field of research, and we know of at least 5,000 other planets outside of our solar system. So at least 4,000 stars outside of our solar system have planets, and so Giordano Bruno's prediction has come true. Albert Einstein predicted that masses must bend light. Again, this was a theoretical prediction. And Roger Penrose predicted that matter must collapse into a black hole when the mass exceeds a certain value. So these are some examples of theoretical predictions. Now, observing the cosmos, astrophysicists use the whole electromagnetic spectrum, right from radio frequencies to microwave, infrared, visible light, ultraviolet, and so on, right up to gamma rays. We also use high energy charged particles which come onto the Earth from the cosmos. We use neutrinos, although measurement of neutrinos is still a field in its infancy, but we have detected them and we do use them. And we also use ripples in the fabric of space-time, which is also a relatively new technology, which is maturing, has been maturing over the last 10 years. Now, the Earth's atmosphere is only transparent to radio frequencies and visible light frequencies, and so telescopes at these frequencies can be on Earth. But if we want to observe the cosmos in the infrared or ultraviolet or X-rays, then the telescopes have to be put in outer space. So these are some examples of observatories. So here is a visible light observatory as seen from the outside. So you only see the building. This is the famous Hubble Space Telescope. This is the Chandra X-ray Observatory. This is the James Webb Infrared Telescope, which is a more recent one and producing enormously fascinating results. This is the Giant Meter Wave Radio Telescope, which is located in Maharashtra. This is IceCube in Antarctica, which detects neutrinos, and this is LIGO, which one of the components of LIGO, which detects gravitational waves or ripples in the fabric of space-time. And each of these is an enormous engineering feat. And you might ask, why do we need to observe the cosmos at different frequencies? So here is Saturn, and on top is a visible light image of Saturn, which you probably have seen through telescopes. And here is a radio image of Saturn. And you'll say, I mean, it looks more or less the same. But if you compare Jupiter, this is a visible light picture of Jupiter, and this is the radio picture of Jupiter. And you can see that it looks very, very different. And the reason it looks different is because we are seeing here not the disk of the planet at radio frequencies, but we are seeing synchrotron radiation from around the planet. And so it turns out that Jupiter is a really strong magnet and accelerates particles and produces this synchrotron radiation. So if we did not image Jupiter at radio frequencies, we would not know that it is a large magnet. So this is one example of why we need to observe the cosmos at different frequencies in order to fully understand the physics of it. So I want to very briefly talk about false color pictures, which is something that we use all the time. Because remember, I said we image the cosmos at different frequencies, which the eye cannot see. So then what does it mean to render those images that which are taken at frequencies that the eye cannot see? So here is an image of a cat, familiar. This I claim is an infrared image of a cat. And this is also an infrared image of a cat, but it looks in different colors. These are both false color pictures. And what that means is that the colors only represent the intensity that is measured. They don't represent the real colors. So we arbitrarily choose some different colors to represent different intensities in these images. And therefore, a false color image makes meaning only when it is accompanied by a key which tells you which color is at which intensity. So these are both the same infrared image, except different colors have been used to render the image, and that choice of color is completely arbitrary. In that context, this is what we would call a true color image, which means that we observe something in the red, green, and blue channels and combine them to imitate or mimic what the human eye would see if it could see this, right? So this is also something that we use quite commonly for visible light images that are taken. And the same galaxy that you see here on top is taken here, is photographed here at different frequencies. This is X-rays. This is again visible light. So this image is the same as this image, actually, but this is rendered as a false color image. And this is the infrared image of the same galaxy. So you can see that in the visible light image, you see this dark band across the galaxy, which is because of a lot of dust particles in our line of sight that obstructs us from seeing the light from the stars in that area. And those dust particles glow in the infrared. So that's how you're able to see this structure for the same galaxy when you image it in the infrared. Again, an example of why we need to image the cosmos at different frequencies, because we learn different things when we do that. Okay, spectroscopy is a supremely important tool in astrophysics research. So you all know, I think, what a spectrum is. Spectrum is basically the rainbow is a spectrum when water droplets disperse light in the sky. The same thing happens with a prism, and if you do it at a much finer level with a spectrograph using gratings, then we can actually discern the fingerprints of the different atoms that might be leading to the emission. I'm sure you've all seen this in your laboratories. So obviously, spectroscopy can tell us what the composition of the stuff that is emitting the light is, because we can recognize the different patterns, the fingerprints due to the different elements. But there's also many other reasons why it is a very important tool. So for example, it gives a handle on the temperature of that chunk of stuff, whatever it is, a gas or a star or something that is emitting the light. And so suppose you imagine you have a cloud of gas, and that cloud of gas is in front of some radiation source, like a star. Then what you would see is a so-called absorption line spectrum. That is, you would see the continuum light in the background, the rainbow kind of thing. And interspersed, you would see these dark lines. And that's exactly what you would see if you, for example, observe the sun using, say, a CD, which can act like a dispersing element. And you will see what are called Fraunhofer lines. I'm sure you've done this experiment before. And instead of seeing it with a powerful source in the background, if you looked at the cloud directly, like this, then you would see the same spectrum but as an emission line spectrum, meaning you would see the lines from the different atoms that are there in that cloud of gas as emission lines. So which emission lines you see depend on um depend on not just the composition but also the temperature, because higher the temperature, the atoms are excited to higher levels and you will see de-excitation from them, so you will see different emission lines. So by looking at the emission line spectrum, we can actually infer the temperature of that cloud of gas or the surface of the star or whatever it is. In addition, spectroscopy is a powerful tool for another reason. You all know about Doppler shift, which happens to sound and which also happens to light. So if a source of light in the cosmos is moving towards us or away from us, and if we can see emission lines or absorption lines from it, then by comparing the frequency of those emission or absorption lines to what we know are the frequencies of those lines in the laboratory, we can measure a redshift or a blue shift, depending on whether that source is coming towards us or away from us. And so we get a handle on the speed of these objects. We can actually measure the velocity in our line of sight, either towards or away from us. That is huge because that is a prerequisite to then inferring things about the dynamics of whatever we are looking at. And then for some of you who might have done a deep dive into spectroscopy, I don't know how many of you have. If you haven't, you can just ignore this slide. But if you have, then it is very, very interesting for us astrophysicists that spectroscopy also gives us a handle on what is causing the excitation of atoms. Is it stars or is it something more powerful than stars? And we do that by plotting a ratio of a pair of lines against a ratio of another pair of lines. And this line, for example, is what we call a high excitation line, which means that the atoms are excited by powerful radiation to very, very high levels. And by plotting this kind of a ratio in a diagnostic like this, we can discern whether the ionization is happening due to stars or whether it is happening due to something else. And in this plot, each of these dots is actually corresponding to a whole galaxy. So all the light from the different stars, the billions of stars in a galaxy all together gives us one of these dots. And so we are able to say whether in a given galaxy, it is the stars that are dominating this process of exciting the atoms or something else. So now, this is the final reason why spectroscopy is so powerful, because as you know, the universe itself is expanding, which means that space-time is stretching. And so the light from distant objects is also stretched. The emission and absorption line frequencies are therefore increased. So we see a much higher wavelength or a much lower frequency due to the stretching of space-time from faraway objects. The further something is, the more the stretching. So therefore, measuring the stretching or the shift in the frequencies of absorption lines or emission lines towards longer wavelengths or shorter frequencies tells us how far these objects are. Because as you can imagine, we are just looking at the sky, right? And we can't just immediately tell how far something is just because it's a shining dot. So we need other ways to determine what the distance to these shining dots are. There could be a shining dot or a shining cloud, whatever it is. And so it is because the universe is expanding, it gives us a tool to measure the distances of these objects. Okay, so now let's get back to black holes. So you remember we played the squeezing game, and we figured that when you squeeze something hypothetically to such a size that even light cannot escape, that is equivalent to being a black hole. But to really understand the physics of black holes, we need Einstein's new way of understanding gravity, which is called the general theory of relativity, which he propounded in 1915. So basically, his theory was that mass, any mass, whether it's your mass, my mass, the mass of this building, your building, whatever, curves space time, which means it curves this fabric in which we all exist. So that is what this equation represents. So this is just constants. This represents that the amount of matter or energy in a given chunk of space-time, and this measures how much that space-time curves. And a scientist called John Wheeler put it very nicely. He said, mass tells space-time how to curve, and space-time tells masses how to move. That is kind of a summary of Einstein's general theory of relativity, simply put. Now, very soon after Einstein put forward his theory, a scientist called Carl Schwarzschild found a consequence of Einstein's theory, which is the same formula that you remember we got from the squeezing game that we played, which is a relationship between the size and the mass. However, at that time, people didn't interpret it that way. They didn't know what this was. It turned out that this consequence actually had what is called a singularity, which means division by zero, etc., which people really didn't like. And so there wasn't much traction to this solution that Carl Schwarzschild found. Even Einstein did not buy it. Several years later, scientists by the name Robert Oppenheimer and his collaborators, they looked at this question again. They looked at very massive objects like stars and looked at what would happen if those stars collapsed after they exhausted their fuel. And they came up with the same consequence. And they correctly interpreted what this formula meant. Robert Oppenheimer said a star at collapse will close itself off from any communication with a distant observer who will only sense its gravitational field, which means that when the star collapses to this size, the size which is the mass, that mass of that star multiplied by these constants, then at this distance from the center of such an object, there won't be any communication of what happens inside it. So we won't get any information of what happens inside this sort of sphere that is defined by this radius. But outside this sphere, we will sense the gravitational field which corresponds to this mass. But the questions about this still continued. People were still not happy. Are these objects really existing? Was it an artifact of the mathematics, and would the matter eventually actually come out? Or could quantum physical effects prevent such a collapse? Were all the questions that were circulating. Then, many decades later, there was a very strange discovery, which I will describe now. So this shows you a piece of sky which was photographed at that time, and you can see a whole bunch of nondescript shining dots in the sky. And most of them, of course, were like stars. So if you took a spectrum, they would show a typical absorption line spectrum that one sees in our own sun. But the object in the center, this object, again very nondescript, again looking like a star, it did not show a spectrum like that of a regular star. Instead, we saw emission lines. Not only that, the emission lines could not be recognized as belonging to any particular element. They were at very strange positions in the frequency plane, and so it was all very strange until an astrophysicist called Martin Schmidt thought about shifting that whole spectrum by about 15%. And when he did that, suddenly all the emission lines fell into place. He could recognize that this was the hydrogen emission line, this was also the hydrogen emission line, this was oxygen, and so on and so forth. So everything fell into place. But it meant that if this shift by 15% was because of the expansion of the universe and the stretching of space time, it meant that this particular shining dot was very, very far away, but still shining as brightly as all the stars, which are much closer, which meant that it was unexplainably luminous. It was so luminous that as much as luminous as all the light from the hundreds of billions of stars in a galaxy put together. That's an enormous luminosity. It was very hard to explain. So Martin Schmidt actually got onto the cover of Time magazine at that time for this discovery. And it was actually worse than that, because the light from this object was also known to change. So that is what you're seeing here. This is the light plotted against time. It was changing on a scale of a few hundred days. Now, astrophysicists have a very straightforward argument to determine the size of an object when we see that its brightness is changing. We call that the light travel time argument. It's very straightforward, actually. So if you imagine an object, a hypothetical object, which suddenly brightens, let's say. So this is showing that it is brightened. We will see from far away from Earth through a telescope, the photons from the front of this object reach us first, and then the photons from the next layer and the next layer and the next layer, and photons from the back of this object will reach us last. So there will be a time difference between the photons from the front and those from the back reaching us, which means that if we see something change on a time scale of, say, t, that object must be smaller than the distance that light would travel in that time t. So since this object was changing on a scale of a few hundred days, it meant that the size of that object had to be smaller than a few hundred light days. Now that's a very small volume. And that made the problem even more difficult, because you needed all this light, which is equal to the total light from all the stars in a galaxy, originate in a very, very small volume of order of our solar system. And that's why George Gamow wrote this little poem. So while all this was going on, there was some theoretical work by Salpeter and by another team called Zeldovich and Novikov in the Soviet Union. And they showed that near the horizon of a black hole, the gravity is so strong that it can be harnessed to produce the kind of power that we were seeing, the power that is brighter than a billion suns. And that was sort of, in effect, what Gargantua is. And with this mechanism, one could explain the enormous power of 3C273. So giant black holes were just what we needed to explain objects like 3C273. And Gargantua has this strange shape also for the same reason, because if you had just a very massive object that was drawing stuff into it, that stuff would get accelerated and therefore heated, and it will shine, and that shine can be quite powerful. But if it is a black hole, then in the central part where the black hole is, one would not see any light, because the black hole itself doesn't emit any light, but the stuff around it would glow. And because it's a black hole and the gravity is so strong that the space-time curves, you would see the light from the backside as well curve and come in our direction. So that is why Gargantua has this strange shape. So giant black holes were just what we needed to explain the enormous power of this strange object called 3C273, which was what then motivated Roger Penrose to put the theory on much firmer ground. And so he showed with some very innovative methods, some rigorous topology and space-time visualizations, that without any of these special assumptions that Robert Oppenheimer and collaborators made earlier, he showed that collapse to a singularity was inevitable. So this firm footing, firm theoretical footing, made people much more comfortable with the idea of black holes. And of course, it meant that the enormous luminosity of 3C273 was explained now. So now we know that the smallest black holes are cosmic. So heavy stars collapse into black holes, just like Oppenheimer showed, when they exhaust their nuclear fuel. And we know about 75 candidates in our own Milky Way by the fact that they are coupled with another star and are gravitationally bound in what we call a binary system. And so we have a handle on how heavy they are, and we can show that they are black holes. And of course, ripples in the fabric of space-time have been discovered for many, many objects now with the Gravitational Wave Observatory. And this is just one sliver of the many such black holes they've discovered. And among the heaviest that they have found are these, 156 times the mass of our sun and 175 times the mass of our sun. Such objects are sprinkled all over the Milky Way and also across other galaxies. And estimates are that there are about 10 to the power 7, which means 10 million such black holes as a result of stellar collapse that are scattered all across the Milky Way. But 3C273 and those kinds of black holes, we call them supermassive. They are different. They're different because they are supermassive, meaning they are more than 1 million times the mass of our sun. They're also different in that they're always found in the centers of galaxies, and they also likely formed by a very different mechanism. So the special thing about these giant black holes, when stuff comes very close to them, is that they become like Gargantua. The stuff is drawn into them, it swirls around and eventually plunges into the black hole, but in the process gets heated to very, very high temperatures and glows. And when that happens, we call that accretion, and that glow, as I explained earlier, is very, very powerful. And so we are able to spot them to very, very large distances, even towards the beginning of the universe. So what are the hallmarks of such accreting supermassive black holes? They are also called active galactic nuclei for obvious reasons. That is a sort of old term. So one hallmark is that they emit light across the whole electromagnetic spectrum, right from radio frequencies through visible light to gamma rays. They emit very, very copious X-ray emission and even atomic lines in X-rays. And they show evidence for extremely fast gas clouds revolving around the center. And we think that these gas clouds are Keplerian driven by the mass of the black hole, and the speeds of these clouds could exceed 1,000 kilometers per second, even up to 50,000 kilometers per second. We cannot see these clouds directly, but they leave their footprint on the spectra of these galaxies. And remember, I told you that spectroscopy is a tool to discern the kinematics of, for example, gas clouds that we observe in the cosmos, and that's how we know that these gas clouds acquire these very, very high temperatures. Uh, I'll skip this slide. Another hallmark of accreting supermassive black holes is that they change, they vary. Their brightness varies at all the frequencies that we observe. Of course, the light travel time argument then gives us a sense of how big the physically emitting, light emitting region is. Another hallmark of accreting supermassive black holes is that not all of the stuff eventually plunges into the black hole. Some of it is squirted out as twin jets of plasma. And that goes out of this black hole system into the galaxy. So here are false color pictures of this particular galaxy. This is invisible light. And this is an image of that same galaxy, the inner square, in radio light. And what you see is, you do see some signature of the spiral arm, but you also see this very collimated kind of emission. And these are the plasma jets from the center of the black hole system. This is another such example where this is a visible light image. So you see the galaxy with the spiral arms, and zooming into the very center, this is a radio image, and you can see this jet. So this is a hallmark of accreting giant black holes. And the majority of such black holes show jets like this, but in a small minority, the jets are launched with extremely high kinetic power. So they are launched at relativistic speeds from the center, and the kinetic power is so large that these jets come outside of the galaxy. So this is the galaxy, meaning the stars, all the stars that are bound. And you can see that this jet is coming well outside the galaxy into intergalactic space. Same way here, this is the galaxy of stars, and you can see that these jets are coming out into intergalactic space. And this is a third such example. It's enormous. This is hundreds of kiloparsecs in size. And we know that this is stuff coming outwards because we are actually able to see the blobs of plasma when we zoom in into the center of such objects. So this is the visible light image, and you can see all the stars, and zooming in shows this jet like this, and zooming further in and imaging at different times and putting it all together to make an animation shows you. So this is real data. This is not concocted or created with computer graphics. This is actually what we see in the cosmos. You can see that the stuff is coming outwards into the space around the supermassive black hole. And in fact, sometimes the speeds that we measure exceed the speed of light. That's not because they actually exceed it physically, but when such jets are pointed very close to the line of sight, then the light from the blobs of plasma reaches us, but the blob of plasma itself is trying to keep up with that light that it itself is emitting, which can lead to this illusion that the speed is higher than the speed of light. And another characteristic is that when two galaxies merge, each of them has a giant black hole in the middle, and those two giant black holes, we think, will eventually merge. And this is an example from my own work where we looked at this galaxy called the Karaf galaxy. You can see the spiral arms of the galaxy, but it has this very disturbed kind of structure. So it's actually, now we know, a merger remnant, as we call them. That is, two galaxies having come together to coalesce to form one galaxy. And therefore, each of their supermassive black holes will also come together. And so we observed this galaxy with different telescopes, an X-ray telescope, a radio telescope, and of course a visible light telescope. And what we found is that in the center of this galaxy, there's evidence for the two supermassive black holes. So this is one, and this is the other, emitting radio light, showing a characteristic spectrum of synchrotron emission. And they both these also glow in X-rays, which is what we see here, which is evidence that these giant black holes are accreting matter. So how are these jets made? So one explanation is that when there is stuff that is accreting around this supermassive black hole, this is only a sketch, of course, there's magnetic fields that are threading that stuff. And the magnetic fields, of course, when the stuff is swirling around the black hole, the magnetic fields will get twisted, and that twist and the tension within it can launch some of that plasma outwards into the jets that we see. So that can explain most of the jets that we see around these supermassive black holes. But you remember these very, very powerful jets that I talked about, where the speed is almost the speed of light. So those jets cannot be explained just by this mechanism. So for them, another mechanism is required, and there what is suggested is that instead of a still black hole, the black hole is spinning. So if you have a spinning black hole and you have magnetic fields threading that region, then it is possible to create jets of plasma that are launched at relativistic speeds. So here is a computer simulation into which these authors have put in all the physics we know, including the general theory of relativity and magnetohydrodynamics. And that simulation shows that indeed this is possible. So the green lines here represent magnetic field, and the colored stuff is stuff that is drawn into the black hole. And so the magnetic fields are getting twisted due to, and can extract energy from the system of spinning black holes. And you can see this blue and red stuff, which is the plasma, which is launched at very, very high speeds, almost the speed of light. There are many examples of this that we know of. This is the only explanation we have to explain jets of plasma close to the speed of light. Now, all this is well, but this is still only circumstantial evidence for the existence of black holes, meaning to say that we think these are because of supermassive black holes, but only because we don't have any other explanation for the phenomena that we see. So what would be direct evidence for black holes? One is this relationship between the mass and the size. So if we could actually determine what the mass is and what the size is and show that this relationship is satisfied, then that would be direct evidence. And the second would be what Einstein's theory predicts, that masses must bend light. So if you had, for example, in this chunk of sky, if you had a black hole somewhere, then what would happen is all the surrounding light, like all this background light due to the stars and so on, they would be distorted and curved due to the curvature of space-time. But you can imagine that this is a very, very difficult proposition. So what about this direct relationship? Well, there was a team of scientists in the USA and also in Germany who tried to investigate this for the center of our own Milky Way, which, as you know, is a galaxy with hundreds of billions of stars, and like any other and many other galaxies that we know of in the universe. So there in Hawaii, there is something called the Keck telescope, which is a very large telescope with a 10-meter sized mirror. And the telescope is at an altitude of 4,000 odd meters. And so with this telescope, they looked at the very center of our galaxy, which is somewhere here. So the special thing about this telescope is that it can counter the distortions of light which our atmosphere causes. So atmosphere sends rays of light in all different directions, because of which an image which should be like one of these points here actually gets smeared out into a very large area. So the sharpness of the images that we get are limited. But in telescopes like the Keck telescope, the mirror is made up of these hexagonal segments put together to make this very large telescope. So what they do is they send a laser beam out into the sky and measure the distortions that the atmosphere is causing, and have actuators behind these segments which adjust them in real time to compensate for the distortions of the atmosphere. So, for example, an image of this is Uranus without that technique, and when you apply the technique, you get this really, really sharp image. And that technique was applied to image the center of the Milky Way, which is sort of close to the spout of the Sagittarius teapot, if you know that constellation in the sky. And so what we are seeing here, each of these multicolored dots is a real star in the center of our Milky Way. And we will see what are how these stars move, because these scientists took images of that region at different times. The date shown here in the upper right hand corner. So they started imaging in 1995 and have continuously imaged since then. And this is what the result looks like. So watch how the stars are moving in the center of our Milky Way. As you can see, they're not moving in straight line, they're not moving randomly, but they're actually going in elliptical orbits, which means that there's something really dark and heavy at the center, which is driving them in elliptical orbits, just like the sun drives the planets in elliptical orbits in our solar system. And not only that, this particular star, which it comes really, really close, it goes merrily on its elliptical orbit subsequently, which means there's no evidence of any kind of collision with this dark object that is driving them. That means that this dark object has to be smaller than the distance of closest approach. Now, if you apply the Keplerian formula to this, you get a mass of 4 million times the mass of our sun, and it's got to be a black hole because it is smaller than this distance of closest approach of the closest star. So there is direct evidence for a giant black hole in the center of our Milky Way. So it satisfies this relationship. What about the second thing of a black hole curving space-time and our being able to measure that curvature of space-time? So this is something I showed you earlier, where the background light from the stars is distorted due to the curvature of space-time of a black hole. This is, of course, very exaggerated. And this is not real, of course. This is what we would expect to see. But you can imagine that this is very, very difficult, because the black hole is dark because there's no light coming from it. And the surrounding sky is also pretty dark. The contrast between this and this is extremely low. So it is something very, very hard to do. However, there was one lucky coincidence, namely a galaxy called Messier 87, which I'm zooming into now. And this is what this galaxy looks like. Billions of stars in it. This is a foreground star in our own Milky Way. This is another, but this is Messier 87. And if you take a picture in radio light, it shows this structure. So there is a jet from the central black hole that is visible in visible light, in radio light, and X-ray light. So it was possible to zoom in even further on the very center of this object by using a technique, interferometric technique, which is that you have multiple radio telescopes like this, and you correlate the output from pairs of telescopes. And if you remember your Fourier transform from your maybe your engineering class, each of these pairs, when we correlate the output like that, is measuring one Fourier component of the Fourier transform of the sky. And so if you measure many such Fourier components, it is possible to put them all together and do the inverse Fourier transform and get the image. So for this particular object, Messier 87, an experiment was done with telescopes located at all these different locations and interferometry done with each of those pairs. So this interferometric technique itself is not new, but what it has been there since the 60s, actually. That is how we got all those images that I showed you earlier. But what was special about this was that it was done at millimeter frequencies, which means you get the highest possible sharpness of the images, and the telescopes were located at all these different positions on the planet. And putting all of that together and doing the inverse Fourier transform. So this is Katie Bauman, who headed the algorithm team that did this whole calculation of the inverse Fourier transform. And what that resulted in was that we zoomed in to the center of Messier 87 almost 1,000,000 times. And the result was the silhouette of the supermassive black hole. So here the contrast is much higher because you have all this stuff which is swirling around the black hole and glowing. And that glow leads to a very high contrast between that stuff and the black hole itself. And so this was completely consistent with what Einstein's theory predicted. Indeed, that is the shape that Gargantua has. So that is again direct evidence for the existence of the black hole. And the same thing was done for the black hole in the center of our Milky Way. Remember, I said that Andrea Ghez team and Reinhard Genzel and team found the mass of the black hole for the center of the Milky Way using the stars. Now using this other technique as well, the silhouette of that same black hole was measured. And all of this is consistent with computer simulations, which put in the physics that we know, general theory of relativity and magnetohydrodynamics around the black hole of that kind of mass, and everything is consistent. So I've come to the end of my talk, and I want to emphasize that science, of course, is this thrilling exploration about understanding nature. Science, you have to remember, is not about embracing the fruits of technology. Science is about critical thinking, so critiquing technology. And science is also about being at ease with uncertainty, being at ease with not knowing, knowing that eventually we will get there somehow. And science is about rejecting revealed truth. It's about being willing to change our conclusions based on the evidence. So only as much belief as there is evidence. So this is the kind of awareness that some of us are trying to build by observing the 20th of August as National Scientific Temper Day. You may ask, we have National Science Day on the 28th of February, so why do we need National Scientific Temper Day? The reason is that 28th of February, National Science Day, is all about showcasing the accomplishments of science. Not so much talking about either the failures of science or the pitfalls of science, and it's not about scientific thinking for everybody. So this is why we observe 20th of August as National Scientific Temper Day, to build the idea that scientific thinking has got to be a way of life. It is not just for the laboratory, but it is for everybody as a way of life. And in that context, I want to urge all of you to set aside the 7th of September on your calendars, because that night is going to be a total lunar eclipse. The uh, eclipse will happen around midnight. And you probably know that during a total lunar eclipse, the moon just doesn't disappear. It acquires a beautiful copper color. And this particular copper moon is something that will be visible to 6 billion people, most of them in South Asia, but also around. And it's a very, very interesting reason why the moon doesn't disappear during the eclipse, but instead acquires a copper color. I won't dwell on it here, but I would urge all of you to set aside the 7th of September to have a beautiful picnic outdoors at midnight and enjoy the copper moon. So thank you, and I'll take questions now.
Hello, ma'am. Ma'am, my question was that when we saw the image of the black hole in the center of our Milky Way, then why was the densities toward us was higher and towards the back of the part was low in that image?
Okay, so yeah, so the for the Milky Way black hole, actually, it's not very clear. It was a very, very difficult experiment. So the scientists are not 100% confident about that effect. But it's not very difficult to understand, because the matter which glows is the matter which is drawn onto the black hole, and it swirls around the Milky Way. So are you able to see me, or?
Yes, ma'am, we're able to see you.
Okay, so the matter is swirling around. You don't expect all that matter to be, of the same density and so on. So you would expect some sort of differences in the brightness that we see, but whether that corresponds to this, that is not very clear, because it is not although the shape that they measured and all that, they're confident about that, but they're not as confident about this change in the brightness. On the other hand, the other silhouette of the black hole that I showed you, that it's a much more robust result. So there, the variation, one side is brighter than the other. That we do think is because of the movement of the stuff that is glowing. So when you have stuff that is moving due to Doppler shift, if the movement is perpendicular to our line of sight, then we won't see any change in the brightness. But if the stuff is moving towards us, then we expect a blue shift, which means that we expect we expect higher emission at higher frequencies. So if the actual stuff is emitting at some frequency, what we will see will be blue shifted emission, but we will also measure more photons per second, because the speeds are very high. And so the number of photons per second that are emitted by the material will appear to us as a larger number of photons per second. And so we will measure a higher brightness. Similarly, the stuff that is moving away from us will have the opposite effect. So there will be a brightening of the stuff that comes towards us, and a dimming of the stuff that goes away from us. And we think that is what we're seeing in the case of the silhouette of the black hole of Messier 87.
Got it, ma'am. Thank you.
Hello, ma'am.
Yes.
Ma'am, I was asking, black holes are essentially dead stars who started to collapse on its own, right? I mean, they are shrink to such point that they had that mass radius ratio. So why do they stop shrinking? I mean, like they are stable. The suns do circles around it. So why shouldn't they just stop existing? Like poof, gone. I mean,
Sorry, shouldn't it be what?
I mean, those dead stars are shrinking on its own, right? They are going smaller, smaller, and smaller. So essentially, the radius should go zero, and then they should just disappear.
So the theory predicts that when there is no so if you take a star like our sun, that will not become a black hole as per the theory, because it has not that much of mass. So when its nuclear fusion is exhausted, it will collapse. But if you've learned about electron degeneracy, I don't know if you've learned about that. If you have electrons with a certain, you can't have two electrons have exactly the same parameters. They cannot occupy the same energy and the same spin and so on. So there is something called degeneracy pressure, which means that the electrons will be exerting a pressure on each other, which is able to counter the gravity. So a star like our own sun does not have enough mass to become a black hole. Instead, it will collapse into something that is called a white dwarf, where the degeneracy of the electrons hold its size. So it will not glow. So such a white dwarf will glow to begin with, but it will slowly cool off and so on. And we won't then, after a point, we won't see it. Now, if you take a star which is somewhat heavier than the mass of our sun, say 3 times as heavy or 4 times as heavy, then that electron degeneracy pressure is not sufficient to counter the gravity. So when such a star exhausts nuclear fuel, it will collapse, but it will collapse even further. But it will collapse to a point where neutron degeneracy pressure will come into play, and it will become what we call a neutron star. That is still not a black hole. It is a star, which is a solid object, and it will have a surface and everything. It's like a solid object. Now, if the star is even heavier, let's say 10 times the mass of our solar system, of our sun, then when its nuclear fusion is over, it will collapse, and there the neutron pressure is also not enough to counter the gravity, so it will collapse into a black hole. Now, this idea of a black hole, that size, that is just a surface. It is not a solid object. However, as I said earlier, we cannot get any information from inside come out. Light cannot come, no information can come. So we don't know what happens inside that surface. So as far as we know, that mass will collapse into that size, which is given by the formula, that relationship between the mass and the size. And that is a surface from which no information can come out. And there is no reason to believe that that will further shrink into a single point. So that is one thing. The second thing is the supermassive black holes that I talked about, which are found in the centers of galaxies and which weigh more than 1 million solar masses. They are not the result of stellar collapse. They cannot be the result of stellar collapse. So we think that there is some other mechanism which leads to their formation. Originally, it was thought that in the very, very beginning of the universe, when the stars formed, they were massive stars, maybe 100 solar masses or 200 solar masses, and then the universe was smaller at the time. These stars, due to random motions, would meet other stars, coalesce, and form bigger black holes. And over the billions of years, these black holes grew and grew and grew to sizes of millions of solar masses. But now that understanding has been called into question, because we are seeing giant black holes, evidence for giant black holes, very, very early in the universe, when a few 100 million years after the beginning of the universe, which is not enough time for this process to happen. So we think there's a different mechanism that is leading to black holes. These black holes, we think that it could be that you have a giant cloud of gas, which collapses, and instead of fragmenting and producing stars, under certain conditions, this giant cloud can directly collapse into a single black hole, maybe 10,000 times the mass of our sun. And so if that happens, then there is enough time for it to coalesce with other such black holes and build up and lead to a million solar mass black hole by the time that we see these things.
Ma'am, earlier you had mentioned there being magnetic fields around the black hole. What causes those magnetic fields to originate?
So there's a generation of plasma, because when stuff approaches close to the black hole, it is drawn into the black hole, and so accelerated very heavily. And that acceleration causes the stuff to heat, because there's a lot of friction that is generated between the material, and that heat is enormous. So temperatures of 10 million degrees or higher, and at that temperature the material becomes plasma and generates magnetic fields.
Ma'am, is there information of interaction of dark matter and black holes?
No, that's a good question, but that's fine. No, we don't have any what shall I say, examples of where we think that is what is happening.
And ma'am, what about the expansion of universe with reference to black holes? The expansion the expansion which is due to the outward pressure, ma'am, because in this for black holes we say the universe is the space-time fabric is compressing like a whole downwards, but it is also expanding.
Yes, so the space-time, the universe stretches space-time, but not the space-time around bound objects. So it is the space-time between objects is stretched.
Ma'am, I didn't understand. Ma'am, I was asking that in for the black hole, we say the space-time. If we imagine a 2D plane, we say that it's like a hole. It's just it keeps getting towards the singularity. The space-time curvature is going towards the singularity, but it is also expanding, right? If we take any 2 points,
so
so it has to be objects.
Yeah, so it's not just black hole. Any mass, the space-time curves around that mass. So whether it's your laptop or your building or you or the earth or whatever, any mass, the space-time around it will curve. Around a black hole, it curves more than much more than the curvature due to like everyday objects around us. But the universe expansion is between objects. So the space-time between gravitationally bound objects stretches.
Got it, ma'am.
If
So
the
I have
gravitational
to stop in about a minute, okay?
if the gravitational pull of a black hole is so strong that even light cannot escape, then why is the accretion disk not absorbed by it, not sucked into the black hole?
It is sucked into the black hole. It is just that, just 1 second. Okay, I can do this for a bit longer. I just found that out. Yeah. So see, if you have, let's say, a black hole, and if you have some stuff which is headed towards it directly, then that will plunge into the black hole. But typically, stuff is not headed towards something, right? It has its own speed in some direction. So it's going along at its own speed and then gets drawn into the black hole. So it spirals around the black hole and only then plunges in. So eventually, most of the stuff will plunge in. After spiraling around and then coming closer and closer, getting heated, glowing and all of that, and then eventually it will plunge in. Some of the stuff will not plunge in because it becomes this plasma which is squirted out by the effect of the magnetic field, which is spreading this, it sort of creates that funnel. If you remember that simulation that I showed you, it's almost like it creates a funnel and squirts out this. So some of the stuff is squirted out, but most of the stuff will swirl around and eventually plunge in. So the mass of the black hole will keep increasing.
If as other scientists such as Dr. Stephen Hawking have said that the physics as we know it breaks down within a black hole, what does that even mean? For that I cannot comprehend. What does it even mean?
Well, you should ask that to a theorist. I don't do theory of black holes. What it means is that event horizon that we call, that surface, which is GMM by R squared, that surface, it's a surface from which information cannot come out. So we don't know what is happening inside that surface. But there is a lot of speculation. There's no evidence, but there's a lot of speculation as to what happens inside a black hole. I would direct you to the website of somebody called Andrew Hamilton in the University of Colorado. He has a whole ton of amazing visualizations, etc., on this question, like what happened inside a black hole. But it's speculative because we don't have evidence for it.
Got it.
Ma'am?
Thank you.
I mean, is it at least theoretically possible to move fast enough so as to gain enough mass to actually form a black hole?
I don't think so, no.
I mean, at least according to the Einstein's mass equation, I mean, is it like at least possible to move fast enough so as to gain enough mass to actually form a black hole?
I don't think so. That is not a question for me. I'm not an expert on that. I actually study what we can see, and I am an empiricist. So I test predictions with actual data. So in my understanding, that's not possible, but you should talk to a theorist.
And one more question, ma'am. And how can we contrast between like an event horizon and a cosmic event horizon?
No, I don't understand. How do you mean?
Like the difference between an event horizon and a cosmic event horizon. Like, is there any difference between both the terms, or like
I
mean the
don't
same?
know. I don't know what you mean by cosmic event horizon. What do you mean by that?
It's like when actually like the particles get sucked in like into like supermassive black holes or something. I'm not quite sure, but I've heard of the word. So
No, I don't know what that means. Sorry.
okay, thanks.
Event horizon is basically defined by that formula that I showed you,
Yeah.
which is a consequence of both Einstein's general theory of relativity, and you can also arrive at that same formula using that squeezing game that I mentioned, using Newtonian physics. That is what defines an event horizon. So for a given mass, the event horizon is at a specific distance.
Yeah, thank you, ma'am.
Ma'am, right now, ma'am, you said that objects will eventually fall into a black hole. They will spiral down. Then, ma'am, so we cannot have an orbital velocity with respect to a black hole. Like generally, we have the orbital velocity for a planet or a star.
You can, no? I showed you that. I showed you those data from the center of our Milky Way, where the stars have orbital velocity around the black hole.
So, ma'am, what are you talking about? The objects which will eventually spiral down and enter, or it can be the case. You were saying that it can be the case. The object will eventually spiral down and go.
Yeah, eventually they might. I mean, these are stars which are quite far away. They're not that close that they would plunge in, but the very close ones might eventually, if they lose energy and that sort of thing. Yeah.
Yes, ma'am, got it.
Ma'am, so our solar system is also under effect of some black hole, or are we just way far from it?
We don't have evidence for a black hole very close to us. No.
Okay, thank you.
Good evening, ma'am. Ma'am, I heard this term about that black holes eventually also die. I think some Hawking radiation it's called.
Huh.
That they expel their mass. Ma'am, what is it? If you would explain.
Okay, so I can't explain in detail what Hawking radiation is. Hawking came up with this theory where he used quantum physics and saw what would happen to particles very close to a black hole, and said that there could be this phenomenon where a black hole, quote unquote, evaporates. Now, the prediction of this is theory. This has never been observed, and it's not that easy to observe also, because the prediction is, as per the theory, the bigger the black hole, the slower, the lesser the radiation, the slower this evaporation process. So for the kind of black holes I talked about, the giant black hole, the evaporation process is very, 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 very slow, much larger than the life of the universe. So it's not observable. For stellar mass black holes also, I mean, they're too big for it to be. So it would be really observable for very, very small black holes. And so far, that has not been observed.
Thank you,
Ma'am,
ma'am.
ma'am, how close are we to actually harnessing the benefits of studying black holes and other cosmic bodies? Like, apart from the scientific pleasure, but like actually like affecting general people, how close are we like to harnessing the benefits?
What do you mean by benefits?
I mean, like some scientific like some technological developments or something, like something on that line probably.
I mean, I don't know what you mean by benefits. We are studying objects which are very, very far away. The Milky Way black hole, for example, supermassive black hole, which is the closest supermassive black hole to us, is 26,000 light years away. There are a lot of stellar mass black holes which are much closer, but they are also many, many hundreds of light years away. So the benefit, I don't know what you mean by benefit, but I think what astrophysics teaches us is to have a broader perspective about life, about humanity, about thinking about the cosmos as a common heritage of all of humanity, because we all see the same thing, right? No matter where we are, what our background is, whether we are tall or short, or sitting in India or in Ghana or Australia, we all see the same cosmos. And so it's a reminder of our common humanity. It's a reminder of how humanity has this common heritage. And it is also a reminder of how, in a way, insignificant we are and how small we are. We are just a speck in the universe. And so it leads to a certain philosophical understanding, which I think can improve our thinking and how we approach life and how we approach our fellow human beings, and so on and so forth. But the way you worded your question, it's as if you want, like from a waterfall, we generate electricity. You want to generate some electricity using black holes. That is not going to happen.
No, ma'am, I didn't actually mean that. But anyways, on the same line, I would like to ask you, like, how do you deal with all the uncertainty? Like, I've gone through many books and like many journals and all stuff, but whenever I read about cosmology and all stuff, I tend to actually break my head at the end, like seeing all the vastness of the universe and all stuff. How do you actually deal with the uncertainty and the sense of not knowing? Like, we just do not know even like the 0.11% of what we're actually today. So how do we actually deal with that and move forward into making progress?
That's a good question. Actually, for me, that's a positive thing, because for me, it has taught me how to be at ease with uncertainty. So we get trained to not be uncomfortable with ignorance and uncertainty, not to fear the unknown. So, in the olden days when our civilization was much younger, people had a sense of fear of the unknown. So then, it resulted in a lot of mythology, even with respect to the cosmos and with respect to a lot of natural phenomena. People feared, people feared comets, people feared floods, all kinds of things. So there was that fear because there was no understanding. Whereas when you get trained in scientific thinking and in science, you get much more at ease with uncertainty. So uncertainty and ignorance breeds curiosity rather than breeding fear. So this, I hope, is something that all of you will learn when you are going through your education. And actually, it's something that everybody should learn. It should not need formal education for everybody to learn. It has not happened. That's why I talked about this National Scientific Temper Day and all that. In fact, India is a country where I think it's the only country, at least I know, where people with education, very high levels of formal education with PhD certificates and everything, are still bogged down by fear over certain natural phenomena. Even the most simplest, like I talked about this total lunar eclipse. I mean, I come from Bangalore and I live in Bangalore, and during eclipses here, even though Bangalore sort of is very proud of being an IT city and all of that, so with people with very high levels of education and all that, during an eclipse, all the people of the city huddle inside their homes, don't come out and enjoy eclipses, and just watch it on TV. So this is a specialty of our country. I've not seen this among educated people anywhere else. And so we need to, I think that is what science teaches us. It teaches us to be curious about the unknown rather than be fearful of the unknown. So yes, in the what cosmology has taught us is that we only understand about 4% of the universe. There's about the rest of it which we don't understand. There's dark matter, which we know is there. We see how it behaves, but we don't know what it is. And then there is the rest of it, which we call dark energy, but because we don't know what it is even. We don't even know how it behaves. We know nothing about it. It's just called dark energy. That's just a term. We just don't know anything about it. But not knowing should actually breed curiosity rather than fear. Break your head, yeah, of course. We all break our head when we can't solve a puzzle, right? I mean, that might be a simple crossword. I mean, I have sometimes broken my head over a crossword because I couldn't solve it. But yeah, I mean that's part of the process.
Thank you, ma'am.
Ma'am, can you please shed the light on importance of astrophysics and the effects or importance of astrophysics for a common man or commoner? Like a lot of time people, when we see the research or let's say Chandrayaan or any mission, so the people ask the question is that why are we spending so much money on understanding these things? So can you please shed the importance on that?
Yeah, I think it's a very legitimate question that they ask, and it should be, these kind of questions should be answered democratically. So when it should be a decision that is taken by a large section of the population, because these are things that are funded by all of them. So they have a very legitimate right to ask that question. And I think the answer is partly curiosity is a natural tendency of human beings. So it is important to nurture curiosity, push the frontiers of knowledge, just like dancing, singing, playing games. All of these are natural human tendencies, so it is important to nurture all of them. But whether something like Chandrayaan should be given bigger importance than, say, teaching music to everybody, that is a question that should be discussed and debated upon and decided upon democratically. I need to really go now. within 10 seconds or so. So that is what I would say. And one important lesson from that argument, one important corollary, is that it doesn't make sense to push the frontiers of knowledge in a competitive way. So it doesn't make sense to say, okay, such and such country has done such and such thing, so we should also do the same thing. That doesn't make any sense. That's waste of resources. So everybody across the world should be collaborating rather than be competitive with each other, and push the frontiers of knowledge together, because knowledge is a common good. It belongs to all of humanity. So we should all collaborate and push the frontiers of knowledge together. I really have to go now.
Thank you, ma'am, for giving the talk and such an insightful talk, especially. It was an honor to host you.
Okay. Thank you.
Thank you, ma'am.
Thank you, ma'am.